Senhor Shintani, por favor.
Do you hear me? Yeah, thank you, Mr. Chairman, for the introduction. Although, because I didn't use the headset, I didn't understand what you said, but probably I believe that you introduced me. Am I correct? Now, as mentioned before, the globe or the Earth is covered by ocean for 70% of its surface, like this. I took this photo from the outside of the globe. I tell you how I could take this photo from outer space later. When you use a computer graphic, not this real photo, but using the computer data, you can describe the surface. Oops, where is it? Like this. And this is the computer graphic of Japan with the bathymetry from above the 3,000 kilometer. And now I tell you the result from the UNCLOS Continental Shelf Survey. Our UNCLOS Continental Shelf Survey was made for 25 years, and the result was just lodged to the United Nations CLCS, Commission of the Limit of the Continental Shelf, the Japanese submission. But the result is not only for that submission, but for the science and the earthquake research, volcanic eruption research, and also mineral resources and hydrocarbon resources. The amount of the data and quality of the data brought by the UNCLOS survey was enormous. And I tell you that the amount of the data. But today I tell you the outline of the UNCLOS survey and some of the scientific outcomes are related to the mineral resources. Now we are here, and this is the route I will fly tomorrow evening back to Japan. Some of you may not know where Japan is, but it is around here. And Tokyo, the capital, is located here. For your information, my house is about 100 kilometers, or 60 nautical miles north of Tokyo, and it takes 2 hours, 30 minutes one way. So 5 hours commuting every day. I work only 3 hours a day. Now, I brought this map to explain the geological setting. This is Asian continent, and this is Pacific Ocean. And this is Japan Sea, this is Sea of Okhotsk. And this is Kurill Trench, and Japan Trench, and Izu Ogasawara Trench, and the Mariana Trench. The pointer? Okay. The world's deepest spot is here, a Challenger Deep. These trenches are divided by the shallows, which is shallower than 6,000 meters, like here, and like here, each by the subducting seamount. Thank you. Here is subducting seamount, and here is subducting seamount, and also here. And they are the divider of the trench systems, the name of the trenches. And we also have the Nankai Trough, which is the same thing. It's also the plate boundary and subducting boundary of the plate. But because it's not as deep as 6,000 meters, it is called trough, Nankai Trough. And here is Nansei Shoto Trench, or Ryukyu Trench. Around Japan, there are deeps and deeps and deeps. Now, here is the trench of the Kuril Trench, and Japan Trench, Izogasawara Trench, and the Mariana Trench. All the continuation of the trench system makes the boundary, western boundary of Pacific Plate. Nankai Trough and Nansei Shoto Trench and other boundary delineate the Philippine Sea Plate. And here is something. The Pacific Plate moves at 10 centimeters per year at the northern part of Japan and 5 centimeters at the southern part of Japan. The Eurasian Plate is shown, and let's see, it's frozen. Frozen. Oh yes, start moving. And here is the triple junction of trench, and the depth is deeper than 9,000 meters. It is only 200 kilometers from Tokyo. It's surprising that a trench of the deep of 9,000, deeper than 9,000 meters is located really close to a city like Tokyo, which is dwelled by 12 million people. The Philippine Sea Plate moves at 5 centimeters per year, 5 centimeters per year here, whereas the movement here is almost stable. Mount Fuji, some of you may know, is located here. It's the highest mountain as a volcano, and it's the tallest mountain in Japan, and it is on the plate boundary. If you know ukiyo-e, this is Mount Fuji, and this is exaggerated tsunami. It's not exaggerated. And here is North American Plate, and nobody knows the real boundary between Eurasian Plate and North American Plate. The geologists and the geophysicists and the geodesists say different things. Geologists say from geological side, geophysicists say from geophysical side, and geodesists using the GPS data say different thing. But it is assumed that this line is the boundary between Eurasian Plate and North American Plate. Now, Japan is divided by 4 different plates, and they are active plate. It's not sleeping plate boundary, like 10 centimeters per year, 5 centimeters per year, and so forth. This is a slow plate boundary. It's not visible speed difference, but still we have huge earthquakes every couple of years of the magnitude 7.9 or 5.2 or something like that here also. Okay, the history of continental shelf survey in Japan started right after the adoption as UNCLOS in 1982, in December 10. In 1983, Japan started the Continental Shelf Survey, CSS, by Japanese Hydrographic Department, which I belonged to. Well, I didn't introduce myself. I'm sorry. I belong to the Cabinet Secretariat and taking care of the Continental Shelf submission. But my real background is geophysics, and I got my job in the hydrographic department, and I was bathymetry scientist of the deep ocean. I'm a real bureaucrat now, but it's only 5 years. I'm not an experienced bureaucrat, the beginner. In 1994, UNCLOS came into effect, and in 1996, Japan ratified. And in year 2002, they started the interministerial cooperation. And it's not only the business of hydrographic department, but the business of all the ocean-related ministries participating in the continental shelf survey. And this year, all the survey was completed, and the submission was lodged on 12th of November. This is the bathymetric map. You don't see any bathymetry. It is before you reveal the ocean water. Once you reveal the ocean water, you see the sea bottom like this. The map was built in 1971. This area was mapped previously by JEBCO and Japanese scientists. This is a series of JEBCO maps. If you don't know JEBCO, it is General Bathymetric Chart of the Ocean, which was initiated by the Prince of Monaco in 1903. And this is the first edition in 1903. And here already the ridge system is described, and also the trench. And after that, series of the publication was made, and the data was increased significantly. The recent nautical bathymetric chart around Japan at this area is published by Japanese Hydrographic Department. And they are in several different scales, like 1 to 3 million, 1 to 100 million, 1 to 500,000, and 1 to 50,000. It is a very detailed map. Now, the Continental Shelf Survey started in 1983, and up to 1997, the footprint of the multi-beam survey, multi-beam track was like this. There was some problem on this. The problem is, okay, here. If you look at the map here, it looks nice, detailed. But once you look at the truth, which is the footprint, it's only this. The white area are not surveyed. There was no data. And the computer and the knowledge of the human compensated the data lack, which is okay. In most bathymetric charts are like this, or worse. But for me, the director of the Continental Shelf Survey could not accept this fact here. When I was in charge, I was appointed the director of the Continental Shelf Survey. I got a map like this, but the real footprint was this. It's really, it's not a science, it's an art. And I'm really bad at art. I want some kind of science. And I decided to send our ship again there to show the difference. The area was resurveyed. The right one is the previous survey, and the left side is the complete survey. From your position, they look almost the same. Not big difference. But when you look at the footprint, it's like this. And when you make A minus B, what happens is like this. For this big difference, you skipped, here is a seamount here. You didn't catch the summit of the seamount. You only captured the foot of the seamount, or the flank of the seamount. And so because you missed the top summit of the seamount, the difference is as big as 2,000 meters. It's the difference between art and science. When you don't cover the entire area in the enclosed system, you will lose an area like this. If you don't survey, you only get up to here. You don't get this one. This is a strong message to politicians. That's why I got the funding to make the complete survey like this. The entire survey result up to 2006 was like this, and by year 2008, the sea bottom data of the full SWOT is better than this. And we also got the magnetism data and gravity data as well. For this area, it's quite different from Brazilian coast. Our coastal area, because of that plate motion and subduction and collision and everything, the sea bottom is really complex. In the United Nations Conventions of the Law of the Sea, the definition of the continental shelf is all related to the word foot of the slope of continental shelf. And usually it is the foot of the slope, but for here, the foot of the slope is quite difficult to define. The reason is the convention thought that the sea bottom looks like this, like northern Atlantic. Here's shelf and the continental slope and rise and deep ocean floor. And this is the foot of the slope. However, in Japanese case, the same depth difference from 0 meter to 4,500 meters, 5,000 meters. The maximum change of the gradient is here, but here are many different maximum change in gradient. For us, for Japan, it is not quite easy to apply the convention text. That's why we started a very intensive survey from year 2004. For example, the seismic lines previously planned was like this, but after 2004 up to 2008, the total seismic lines, including refraction of using OBS and multi-channel seismics like this, big increase. And boring, we have boring machines, and we had this much data, but at this moment, the amount of the boring spot at boiling points is like this. The game players for this intensive survey was like hydrographic department, and JOGMEC, it's a Japan Oil, Gas, Metal, something. And Geological Survey of Japan, and Japan Marine Science Technology something, JAMSTEC. Hydrographic department is basically working for safety of navigation, and they started the Continental Shelf Survey since 1983. JOGMEC is a resource related organization, hydrocarbon resource and mineral resources. And they joined the Continental Shelf Survey from 2003. Geological Survey, they are geological scientists joined from 2003. And JAMSTEC, they are working on ocean science, and they started to join the Continental Shelf Survey business in 2004. Hydrographic department did bathymetric survey, geophysical survey, and seismic surveys. GeoGMEC, bottom sampling, geological survey, again bottom sampling, and JAMSTEC, seismic surveys. Hydrographic department used 2 ships of 2,600 tons and 3,000 tons. And also contractors brought the seismic vessel. I think it's a very good seismic vessel. And GeoGMEC and geological survey used Hakurei number 2. This came with the BMS, benthic multi-coring system, or boring system. It's like this. The machine has 12 cores of 4 meters each. And by joining the core, it can take 20 meters of cores. Usually you can, as an average, you can get 10 meters of cores for each point. And the maximum depth of the operation is 6,000 meters. So you can bring this machine to the depth of 6,000 meters and the core, get the core sample up to 10 to 20 meters. Which is, the purpose of using this one is to get the